This is question number 1, a practice well. It's an old exam, number 3, from spring of 2013. So this is for review for other students. So on the graph of F in the figure below, indicate the X values that are critical points or points of inflection, label whether they're max mins or points of inflection. So this is spring 2013. First of all, I want to know the derivative is flat. The derivative is flat here and here and here. So these guys are critical points. So let me see, I should have some kind of notation. These guys, so this equals critical point. Alright, or points of inflection, aha. But there's actually, I did not expect people to get this last year. I expected people to get most of this. I expected people to notice this point of inflection, which is also a critical point. But I was hoping that they would notice this point of inflection and this point of inflection. So the grading scale was such that if you forgot those two, it didn't kill your progress on this question. But you should realize that you're either spilling water or holding water. Spilling water or holding water. And the whole curve can be broken up that way. Everywhere spilling water and holding water transitions, that's going to be a point of inflection. Okay, so let's see, we want to label whether they're max, min, it's a local min, not the absolute min, point of inflection, point of inflection, point of inflection. That's what they are. Okay. Then on top of the plot of f of x, plot f prime of x. So at all these critical points, we have assurance that we're going to be on the axis for f prime. Everything up to, let's say, maybe negative 0.7 or something, maybe negative 0.8, I don't know, maybe negative 0.8. Everything up to there is going to be increasing, so it's positive. So we're going to be coming in like this. But then everything between there and the origin is going to be decreasing, so it's going to be negative. But the point of inflection is going to tell where it's decreasing the worst, so it's right about there. And then what happens? Even though we're approaching 0, we're not going to be crossing through, because what's going to happen? There's this rotational symmetry, and everything is happening the same down here. So this point of inflection tells where the deepest, the steepest slope is. Think about it this way. If you're a car and you're driving along, this point of inflection that I'm pointing to now, that guy is where you're most likely to have your car slip if it's icy. That's one way to think of a point of inflection. Although, okay, here, at this point of inflection, is where your car is least likely to slip. But the concept's actually the same. So most or least likely to slip. Let's say most or least likely to slip here. That's going to be a point of inflection. Okay? And then here's a question. Assuming that f of x is a polynomial, what's the smallest degree it could possibly have? Alright, the students had trouble with this last year. But you guys, whoever's watching this video, you will not have trouble with this, because you know it's not meant to be a hard question. So the point is, I should probably label this other guy as f. Let's see, f, this gray one is f prime. So what was f prime? If f prime looked like this is what degree? Well, it goes down. So a line goes down. A parabola goes down and up. Cubic turns around again. So it's a 4th degree, but that's not f. F prime is 4th degree, or possibly more. There could be more wiggles that are hidden, that are too small for our eyes to see, but it's at least 4 degrees. But if f prime is 4 degrees, then f must have degree 5 or more. Okay? And so you can look at the original function and figure that out, but it's much easier to just figure out that the derivative has degree 4 or more.